I did it. I managed to write two completely different functions that generate identical assembly code. The assembly code on your left is an iterator version of that using Rust iterators. And on the right is a nested for loop that has the exact same assembly code. Now you might be thinking, why is this important? Why is he excited? And I have to admit, I've been questioning that myself, but let's get into this and explain how we got here and sort of why this is important. How we got to this point are these two functions. I was doing a peer review for the advent of code, and I was looking at ways of being able to illustrate how iterators can be an easier or a better way to write software and have your actions be written as iterators instead of manipulating a data structure. So the bottom function, the version, the operation these two functions are doing is to find the y-x position of a character in a two-dimensional array. So if we look at the bottom function, this is doing what we would normally do if we were going to iterate through the two-dimensional grid the way we're sort of taught to do it in computer programming 101. We have two nested for loops, y and x. Y goes through the rows, x goes through the columns. I am using this unsafe version of it just to avoid any benchmarking that would suggest that accessing or doing the checks, out of bounds checks, is causing any sort of performance differences. So again, we go through the y, we go through the x, we get the cell value for each one of those. We're even caching the row reference so that we don't have to extract that every time. And if the cell is what we're looking for, then we return some. Otherwise, if this goes through all the values, we drop out and return none. The iterator version is the same functionality as the nested for loops, but if you are coming to Rust without the mindset of performing operations on your data structures using iterators, this is going to seem a little foreign to you. And you might say, oh, well, I would rather have the nested for loops because this makes more sense to me. And I would argue that you need to make this make sense because as the manipulations of containers become more complex, this representation makes your code easier. So let's look at the assembly for these two functions. In contrast to what I showed you before, these two functions are, the generated assembly is very different from each other. The one on the left is the iterator version of it. And at the beginning of most of these, you're going to have this preamble, which is setting up our register stack and pulling things into variables. And we're going to have then some labels that we're going to be jumping to, sort of representing the inner and the outer loop of our function. The very inner comparison is right here, and the corresponding one in the for loop is here as well. So we're comparing the value that we're pulling out of the grid with ECX, which is where our the value is that we're looking for. And if that's true, we're going to jump to the end and say, yes, we got it. Otherwise, we're going to do the loops. But the contrast here is sort of an indexed based version of a nested for loop versus this version that's generated with iterators. So let's look at the benchmarking just to see what are we looking at? Where are we at with respect to the performance of these two different functions? The criterion benchmark for these two functions is as follows. The for loop version of it takes 32 milliseconds to walk through a 1000 by 1000 two-dimensional grid to find the value in the very last position. And the iterator's position is the function that does it with iterators. And you can see that the version for iterators is notably faster than the one with a nested for loop. And again, to be honest, I'm not actually all that concerned about the difference in speed, except sort of to note that if you think that hand rolling your own functions using for loops because you think that iterators are going to perform less than you can hand code it, you're going to be wrong. And I'll show you that if you want to get identical performance out of your hand rolled functions to iterators, for one, you can't do any better. And for two, it's going to look awful, simply awful. And you're going to be in a load of hurt trying to manage this. So let's figure out how can we get the iterator's position to be identical to a for loop version of iterator's position. So just to recall where we're starting from, this is the version of the function that is using a nested for loop like we would expect in really any computer science class. This is how they're going to say how to write it. They're actually going to probably use this version here, the for loop that doesn't do the unchecked, but just to show that it is the unchecked version of grid or of slice axes is not causing the slowdown. We're using this version and still getting a very measurable, almost 10 millisecond difference between this version and the iterator version. So let's sort of cut to the chase and look at what it takes to write a version of a nested for loop that generates identical code to the iterator version. This is what the iterator version unrolls to when it is as represented still as Rust code. So let's look at what it's doing here. The sort of preamble here is taking the gridlin, getting a pointer to the, let's turn on that, getting a pointer to the first row of the grid, calculating a pointer to the last row of the grid, and initializing our y value to be 0. That's one of them that we're going to return. And the inner loop is doing the same sort of thing. We are dereferencing and getting both dereferencing the pointer and then getting a reference to it to get a sort of pointer / reference to the first row or the next row that we're going to look at. We compute len and the active pointer and the last pointer as well as initializing x to 0. And then while we're not at the end, we do the unsafe dereferences to pull out the value of the cell, and if it does match. Otherwise, we do some additional unsafe pointer arithmetic to get to the next row pointer and to the next column pointer, depending on if we're on the inner or the outer loop. This is what that gets unrolled to. Okay. And this will generate identical assembly for these two functions. So the way that I look at the assembly code is to use Godbolt, the compiler explorer that allows you to put in Rust code on the right hand or on the left hand side, and it will generate for you the machine code on the right hand side. I'm using the nightly compiler, with an op level of 3. This is the same. These are the same options that you're going to get when you're doing fully optimized benchmarking. And with this, we can then look at the code that is generated for every function in their sort of human readable assembly version of that. And when we do this, if we look at the value or at the generated assembly for the for loops, what are we looking for? It's for loops pointers unrolled. So if we search for this, this is the assembly code for this, and the assembly code for the iterator positional one is here. So if I take this assembly code and copy and paste it into my editor and look at it side by side, we see this. And this is the same code that I showed you at the very beginning of our recording that I was so excited about, where the preamble, the loops that are being done is identical assembly code for assembly code, except obviously where the labels are, to each other. This is the identical version of this. So this proves that this is what the assembly code is for the iterator version that is the most optimized version of it. I haven't been able to get this to operate any faster using any other method than what we're seeing here. The two versions that generate identical assembly code are left and right, and I present to the judge and jury, would you rather see in your code the version on the left, or would you rather see the version on the right? And I don't think that there is any I don't think there's any answer that you can give except, well, I think it's obvious. Thanks for watching. Let me know if this helped, and anything else that I can do to enlighten you, please let me know. Thanks for watching.